Okay, let's get started with or continue the lecture, but we're going to talk about logistics. But even before that, takeaways. Basically what you've seen so far, I think it's an exciting time to be understanding and designing computing platforms, because we have many challenging and exciting problems in platform design. We didn't really have this sort of problems until recently, I think. Of course, there were always problems, but the nature of the problems is really changing. This reliability issues, for example, they've started really affecting the heart of computing more recently than before. Reliability was always a problem, don't get me wrong, but technology scaling has brought us to a point where it's very hard to solve the problems just with technology. And people have not tackled or thought about some of these issues before. And even if they have thought about it, they haven't thought about it in the perspective that we have today. So there's a lot more to do. And of course, it can have a huge impact on the world's future, right? If you don't prevent Rowhammer-like attacks, that's not good. That's very fundamental. And also there, on the application side, we have a huge drive for hunger, new applications, even greater realism. There's a lot more to do over there. And we can easily collect more data than we can analyze and understand. We're going to talk about genomics at some point, bioinformatics, and accelerators for it. Mohammed did his PhD thesis, sitting in the back. He's going to give a guest lecture on that. So you're going to see that there are a lot of interesting problems with big data and new applications that we want to enable. And also, as we just discussed, there are significant difficulties in keeping up with that hunger at the technology layer today. Energy, reliability, complexity that are affecting security and other scalability are important. And applications, I think this is, I use this in a lot of my lectures, but applications I'm not worried about. People can always come up with new applications. People are very creative. And over the course of the decades, we've come up with new applications, right? Who could imagine we could do virtual reality, for example? We don't even do virtual reality today, but people are imagining doing that. And there's a lot more in that space. But the trade-offs are becoming different also. If you've taken my seminar course, I use the slide, but I'll use it again. If you've taken digital circuits, you've seen it too. It's a relatively old slide, 2015. All of the technology numbers that you see over here, you can question. But what this shows is a 64-bit double precision floating point operation consumes a small amount of energy. It's actually a very complicated operation, 20 picojoules. A simple DRAM read or write consumes about 16 nanojoules. That's 800x. I'll take the liberty to increase it to 1000x. Basically, a single memory access consumes 3 orders of magnitude more energy than a complicated floating point operation. Now, it's good to ask the question, are we doing things right in a principled way if we're actually bringing all of the data into the processor to process it? Right? Because let's assume that you're doing a floating point addition. You need 2 source numbers. Let's assume that they're in different parts in DRAM. You do 2 DRAM accesses to bring the 2 floating point values into the registers. You do the double precision floating point addition, and you do 1 more DRAM access to write it back into DRAM, write the result into DRAM. That's 3 DRAM accesses for a single simple operation. And assuming that you have a lot of random accesses to data, which you may actually have in real applications, because a lot of the real applications don't have very good locality. As a result, you're wasting a lot of energy just moving data into the processor to do the operation. And if you look at the systems we design today, they're all compute-centric. They all need to move the data into the processor, into the accelerators, into FPGAs, into GPUs. Whatever computation unit you have, they have to bring the data to themselves to operate on it. There's no mechanism to do the operation on the other side, if you will, inside the memory or inside the storage. So this trade-off is very interesting, I think. And today we're designing systems exactly the same way we were designing systems 70 years ago. But 70 years ago, this disparity was much different. Actually, this was the expensive part, and this was the relatively cheap part. This was maybe 2 orders of magnitude more expensive than this memory access. Now, clearly, we moved about 5 orders of magnitude to the other side. This became a lot more expensive. This became red, and that became green. As a result, we should probably rethink the systems we design. And people are actually now open to that rethinking. A lot of people are very open to near data processing or processing in memory techniques because of this. Yes?
How does this compare to reading a value from cache?
Yeah, that's a great question. So if you're reading a value from cache, there you go. This is a 256-bit access from 8 kilobyte SRAM, which is cache. It's only 50 picojoules, as you can see. So the real problem over here is going through that off-chip interconnect. Those are actually very heavy. You need to drive the interconnect, and you need to drive it back. So there's a lot of overhead in terms of energy that happens. On-chip interconnect is not very expensive. But as you can see, it depends on the distance you travel. So for example, going from one end of the chip to some other end of the chip for a 20 millimeter by 20 millimeter chip, it's 1 nanojoules. But that's still about 1 order of magnitude lower than DRAM. Of course, if you trust these numbers. But these numbers are reasonable. Of course, they change with the technology generation and the assumptions that you make, right? So ideally, you would like to keep data local, but modern applications may not have that property. We're going to talk about graph processing, for example. You get a graph, and you have no idea how that graph is connected. That may be formed dynamically. And you may not have the ability to actually reform the graph such that you exploit locality, right? And reforming the graph to exploit locality may actually be very costly to begin with. As a result, you do a lot of random accesses. Okay, so this is a very interesting trade-off that we're going to talk about. We're going to talk about processing in memory in one of the lectures that's coming up. And this is another principled approach, I will say. The principle is we want to be perhaps more data-centric when it makes sense to do so. Basically, currently, regardless of wherever the data is, we're processor-centric. But maybe the principle is do computation where the data is. The data may be in the cache, then do the computation over there. The data may be in memory, do the computation over there. But we don't have the mechanisms to do that. We don't even have the mechanisms to do the computation inside the cache over here, right? Yes, you may do it in the processor, but not necessarily in the cache. Okay, so this is fascinating, I think. This is a new thing that's becoming even more important. And I'll give you the historical perspective to it also when we talk about processing in memory. But this is the time that we're working on computer architecture today. It's very different from the past times. Increasingly complex systems, past systems were like this. I think current systems are a lot more complex, as you can see, and this doesn't do justice to it even. We clearly have many processors, accelerators, FPGAs, GPUs. Some of them are on the same chip. Some of them are on different chips. Memories are becoming more hybrid. GPUs already have high bandwidth memory and then some other memory. That's going to increase. Some systems have embedded DRAM and DRAM. They also have SRAM. And we're having persistent memory and storage. I think Intel's Optane is an example. It's persistent storage, 3D X-point. And they've announced that they will also have persistent memory, phase change memory. I shouldn't say phase change memory for Intel, but basically Optane's 3D X-point that's on the memory channel, that you can access it like memory. It takes time to do these innovations, and we're going to read the paper that has introduced replacing DRAM with phase change memory in 2009. And it's going to happen hopefully in 2019. Right? That's the time frame, and you can see, even with phase change memory, with a technology that we know reasonably well. Even in 2009, we knew it reasonably well. We didn't know the exact parameters, but we know the fundamentals of the technology really well. Okay, so modern systems are going to get more complex. We're going to add more accelerators. In fact, the cell phone that I have, or that you have, is much more complicated than this, right? There's a lot more heterogeneity. There are specialized accelerators, video accelerators, machine learning accelerators, speech accelerators, whatever you can think of. Okay, so basically, given this backdrop, the goals of this course are a lot. It's very similar to the goals of digital circuits. We're going to understand how a computing platform works, so it's going to build upon digital circuits. It's good to know what was covered in digital circuits, or have another course that covered a good chunk of the material. And we're going to focus a lot on the trade-offs, understand how decisions made in hardware affect the software programmer as well as the hardware designer. We've looked at Rowhammer as an example. For example, think critically. I think this is really important in solving problems, and think broadly across the levels of transformation. Because I think this is the kind of thinking that we need. And I think these are the long-lasting parts of, hopefully, this lecture. Even if you forget everything about computer architecture, the approach, hopefully, and the principled approach will hopefully stay with you for a long time. And this one also, understanding how to analyze and make trade-offs in the design. So we're going to look at a lot of comparison. We did that in Rollhammer, for example, different comparisons, comparison of different solutions, for example. And I think apply the above in several design projects. Most of them are design projects right now. They're not research projects. At some point, we may restructure the course such that it becomes more research in terms of projects, but it didn't happen for this semester. But if you're interested in research, you should definitely talk with me. And there'll be homeworks also. So the paper reading part will be certainly more researchy of this course. And certainly the discussion that we have in lectures. But please participate. It's good to have your participation. I know it's a bit dark here. I feel that darkness is affecting people. Yesterday there were more questions. Today it's darker, and maybe not consciously, but unconsciously you're thinking, oh. Okay. So please participate and ask questions. There's a lot of material, and if you leave me, I'll talk for a long time. I can talk about this for hours and hours. Okay, just a little bit about me. Remind me, how many of you have taken my digital circuits course again? Okay, there were more people yesterday. I think they figured they know everything, and they're going to watch the videos. I'm okay. You don't have to come to class. You can watch the videos online. I mean, you're all masters, PhDs. That's true for bachelor students also, basically. You can all decide whether you want to be here or you want to watch the videos after they're posted. Of course, there's a delay between them. You don't get the videos immediately. But I've been here for about 3 years now. I was at Carnegie Mellon before. I still have a research group there. Just to give you the details, we're going to cover my PhD thesis also a little bit. I got my PhD at UT Austin on run-head execution. That was the thesis. And I worked at a bunch of places, Intel, AMD, started the computer architecture group at Microsoft Research in 2006, right after my PhD, and consulted at Google and VMware more recently. And, well, this is the best way to reach me. I prefer my Gmail address, but my ETH address is also okay, no problem. And if you don't get a response to your email, please send it again. They're reliable to issue an email, not just on the email end, but also on my end. And I do research and teaching, as you can guess, computer architecture, systems, hardware security, bioinformatics, and these are some of the areas that my research group works on, and you will see a lot of the examples of the research over here. And sometimes actually we'll have guest lectures from my students, postdocs. They will talk about some of the cutting edge issues that are related to the lecture. And I just mentioned the genomics acceleration earlier. Mohammed has done a lot of work on that area, for example. Okay, teaching assistants, we have a lot. They're not official, all of them. Well, actually, maybe none of them are official because this is a relatively small course, but we have a lot of people that you can consult. As you can see, they're all my students or postdocs. Is everybody here? Maybe I can introduce them. Mohammed is over there. You want to raise your hand? Okay, good. John is somewhere here. He's also in the back. Geraldo is right here. Hassan is over there. Jeremy is not here because he's coming back. He was presenting at a conference in Austin just yesterday, right? Something like that. Juan is over there. Minesh there. Iwan is also in the corner. And Girai is also over there. So there's some locality of teaching assistants, as you can see, in that area. And if you want to access these and them together, there's a random access that you need to make. Okay, so they're going to help a lot with the course. You can talk with them. And if you're interested in any research, you can talk with anyone also. You can see that some of the papers that I mentioned are their papers. So they're doing active research in this area for different topics. Okay, so basically the major high-level goals of this course is to understand the principles and the precedents. I think I've said this before. Based on such understanding, do all of these. I'm going to skip this because we already said that. So I think this course might seem like it's only computer hardware, but as I said earlier, hardware and software are really blending today and merging today. And that's true not from a research perspective, but from a real product perspective also. So if you look at big companies, they're feeling extremely limited by what can do in software. As a result, they move to hardware, all of them actually. If you look at Google, Google is designing systems that have specialized accelerators in hardware, TPU, tensor processing units, right? They have many, many examples of that in their data centers. These are accelerators and hardware. If you look at, which one should I pick? Microsoft, for example, they're already using FPGA accelerators in their data centers, right? They have fancy names for their projects. Catapult is one of the names. The new thing they have is called Brainwave. I think this is basically FPGA-based machine learning accelerators that they built for inference. They have a bunch of other accelerators for training also. And they do actually these FPGA accelerators for their networking infrastructure in the data center to accelerate cryptography operations internally and any other networking operations. Amazon is another example. They're already offering you in the cloud FPGAs. You could actually use them in their cloud. So today, it's an interesting point where software and hardware is merging. You would normally think of all of these companies as software companies, right? But they're not. They're really systems companies. They're across the stack, and they feel the need that they have to do it because there's no other way to get efficiency and performance. And we may actually cover some of those papers. If you're taking the seminar course that I'm teaching yesterdays or Wednesdays, you can see some of the papers are already there. Okay, so basically, world has changed a lot. There is no clear distinction that's going to happen between hardware and software. You really need to know both if you want to be a really good computer engineer, and also the interface between them. You can develop better software if you understand the hardware, and you can design better hardware if you understand the software. And if you can design a better computing system if you understand both. And that's true. I gave you an example from the data centers, but I forgot to give you an example from here. Right here, actually, it's all about hardware and software. And this has been for a long time, and it's going to get even worse. Worse in the sense that there is going to be even more integration between the hardware and software. There are many, many accelerators over here, and things are more co-designed here. Okay, basically this course covers the hardware-software interface and the microarchitecture, but we'll talk a lot about software because of that reason. So what is the required background? These are the expectations. That's going to be a full slide. Digital circuits course, I think most of you have taken. Programming, an open mind, willing to take in many exciting concepts. I think learning the material thoroughly is important. So attend the lectures. I don't care if you watch them online later, but learning the material is the key over here. Doing the readings, doing the exercises and the labs. I think working hard will be important, especially for the labs, because keeping up with the labs may take some time, but it'll be fun. And I think it'll be hard, but if you like it, nothing is hard in the end, right? That's the philosophy, maybe. That's another principle, but that may not be applied to, I don't know if it's applied to computer architecture. I have to think about that. Please participate. I think that's the best way you learn. It's good that you have questions and you ask, maybe propose solutions, different solutions. It's okay if the solution doesn't work. That's fine. Maybe that gets us brainstorming to some other level, right? Perform the assigned readings. Of course, these are obvious, I think. Come to class. I would prefer that you come to class. That's better, I think. That's the better way to learn. You can interact better. Starting early would be important, I think, especially for the assignments. And if you want feedback, come to office hours or find us after the lecture. Or email. Email is usually the best way. I think this is one of my other favorite quotes by Louis Pasteur. Chance favors a prepared mind. Right. And I said this already, I think, earlier, maybe. You have to have preparation and luck. And I think this is the original source of that preparation and luck thing that says, you discover things only if you're prepared. You may feel that you're lucky, but your bias is the coin. Right. If you're not prepared, you may actually see some effect that just passes by you, and you will never be able to discover something. So this course is hopefully there to prepare you, and that biases your coins, and hopefully you'll see the luck as well. Okay, I think how you prepare and manage your time is important. I'm saying this up front because at some point there will be a lot of assignments perhaps. Hopefully they'll be fun, but they will take time regardless. So starting early will help. Okay, I said this already, I think. So how will you be evaluated? Project assignments will cover a lot of the course grade, so they're important. So actually 50% will come from assignments and homeworks. Exams, there will be 2 of them. Actually, we need to decide the time for them. We'll let you know. There will be a midterm exam and a final exam. Do you guys like exams? I guess who likes exams? Who doesn't like exams? Okay, that's a very clear no over here. Well, yeah. I think ETH likes exams. Maybe in the future we'll have more project assignments over here. Okay, more on this later. Okay, what will you learn? Clearly computer architecture. I've said this before. Basically, computer architecture is the science and art of designing, selecting, and interconnecting hardware components and designing the hardware-software interface to create a computing system that satisfies some goals, right? And the goals could be many, as we've discussed earlier, right? So traditional definition is a little bit different, actually. I'll give you some of the basics, and then we'll continue in the next lecture. But traditional definition is architecture is the hardware-software interface. That's really the ISA definition. It's the attributes of a system as seen by the programmer, or the conceptual structure and functional behavior as distinct from the organization of the data flow and controls. So organization and data flow and controls, the logic design and the physical implementation, that's the lower levels. Architecture is what's seen by the programmer. And this is a very old definition. Gene Amdahl's law defined it this way. And that was the traditional definition. But I like this definition more. But if you want to look at the traditional definition, this is architecture, the ISA, right? Okay, we've already seen that. And microarchitecture is something that's below. So we'll hopefully look at fundamental principles and trade-offs in designing the hardware-software interface and major components, focusing especially on memory in this course. We focused a lot on the processor in digital circuits. We're going to focus on the memory trade-offs, and we're going to look at this also. So there will be semester-long lab assignments. We're going to start with the data cache, as I said. It's an RTL implementation. Initially, we'll have 2 RTL implementation assignments, and then we'll go to higher level simulation. And I think that's really important. As a computer architect, you should be comfortable with both very low level RTL implementation, higher level simulation. And they have very different, as we will discuss at some point, they have very different benefits for you in design as well as exploration. If you actually have to implement everything in hardware, you cannot explore a lot, right? If you implement everything in simulation, you'll never get your feet on the ground, maybe. So it's good to do both. And of course, focus on functionality first. So you'll see that the assignments have a functionality component that we ask you to complete, but also there are extra credit parts that I believe are important that enable you to think potentially out of the box, right? How can you design a better cache, for example, not just what's specified over there? Can you design prefetching mechanisms? So you can actually do a lot over here and learn a lot. And of course, you'll hopefully learn how to think critically and broadly and how to work efficiently. Efficiency is very important, I think. Okay, I think I've already said a lot of these, so you can look at that over here. So course website, everybody knows the course website, hopefully. You can go to it from my website. And all slides, lecture videos, readings, and assignments are going to be posted. As I said, homework 0 is posted there. I think lab is posted already, right? Okay, it will be posted after the lecture. And there will be other useful information. So there are links to other courses also. So please check frequently for announcements and due dates. Homework 0, as I mentioned, this is information about yourself, and all future grading will be predicated on this, so please complete it, otherwise you'll get a 0 grade. Okay, some heads up. Basically, we'll have a few required review assignments. They're due likely at the end of the week. Well, at the end of next week, sorry. But we'll see. This is a bit fuzzy. Homework 1 is part of the review assignments. And lab 1 will be, oh, this is wrong actually. This is an old slide copied and pasted from last year. Lab 1 is going to be out today. Okay, any questions about course logistics? Everything sounds good? You're looking forward to everything? Yes, we have one question.
Is RTL like a prerequisite for this course, knowing RTL?
Of course, if you know RTL, then you would do the assignments a lot more easily, but you can learn also. I think there's nothing. You will need to, so in the past, people have taken this course, they didn't know RTL, and they did fine. I should put it that way. Officially, I think it's required in the sense that digital circuits is a required course. And if you take digital circuits, you learn RTL, but unofficially, I don't require it. As long as you're willing to work a little bit harder to learn it, as long as you have good intuition and programming experience, I think you can learn RTL also. It's just another programming language, except it requires a hardware mindset. That's my perspective. But you may find it differently, and if you find it differently, let me know. Yeah. What else? It's actually one of the most parallel programming languages because everything is parallel in hardware. In hardware, you need to think concurrently by nature of the design of the hardware. It's a fascinating language. What else? Any other questions? That's a good question to ask, basically, if you think about like some prerequisites or what you should know, what you should not know. Okay. Let's see. Should we continue with this, or should we take an early day off? What do you think? We can end early today, right? That's a good natural stop point, I think. I'm not sure if I will start with this. I will leave these slides to you. These are some more motivational slides, and then we can start with something else. But I'll decide that. Okay, let's call it early today. I'll see you next week, next Wednesday.